This is the first tutorial in the AQA GCSE revision on radioactivity, and it's called Observing Nuclear Radiation and the Discovery of the Nucleus. Okay, radioactivity. This is the spontaneous and random emission of a particle or electromagnetic radiation (wave) from the nucleus of an unstable atom. The words in bold are key words to this topic, and you need to be sure you understand what they mean. I mean, in a sense, spontaneous means it happens without us controlling it. It will just happen on its own without any input from humans or from increased pressure, increased temperature. The radioactivity is totally independent of any external source. Random, we can't tell what nucleus will decay. We only know that so many will decay in a certain period of time. And the nucleus is unstable, which for us usually means an imbalance of protons and neutrons. We measure radiation with a Geiger-Müller tube, but for the AQA course they seem quite happy to just go with the word Geiger counter. And every time a radioactive particle or wave hits the GM tube, it just registers a count, and you can hear it or you can see the counter as the numbers increase. Okay. Radioactivity, a few key words: aluminium, beta, food and radioactive, and we'll put those into the phrase. So if a substance is capable of always emitting radiation under any conditions, we say it is radioactive. There are three types of radiation: alpha, beta and gamma. These types of radiation are always given off by rocks, food, building materials, air and cosmic rays. This is called background radiation. Each type is capable of penetrating different materials. So we've got paper, then a few millimeters of aluminium and a few centimeters of lead. The alpha particles get stopped just by the paper and also by about 3 centimeters of air. Beta particles get stopped by about a meter of air and a few millimeters of aluminium. And the gamma rays go straight through everything, and indeed are not stopped by anything, but they are reduced by many centimeters of lead. So we can reduce our exposure to gamma radiation, but we can never get rid of that exposure. Okay, background radiation is quite important, and that is radiation from some man-made sources and many natural sources. It varies throughout the country. Usually in the UK it's about 20 particles per minute, and you can't get rid of it really. It's there all the time. Okay, our bodies have kind of evolved to get used to it. So if we have a look at the main sources of it, we find there's radon gas, which is about 50%. It's a radioactive gas which we can breathe in. There's food and drink, which is also slightly radioactive, 11.5% of our background count. Cosmic rays from outer space, obviously great exposure to those if you're higher up in altitude or flying, that's 10%. We find ground, so that would be if you live somewhere like Cornwall, for instance, where there's a lot of granite. You have a slightly higher background count there. That accounts on average for 14%. Medical uses, this is sort of getting to the atmosphere from hospitals and such like, and radiation they use, 14%. And then there's a little 0.5% which is from nuclear accidents, nuclear weapons testing, and if you do a bit of air travel, although that could vary if you travel an awful lot. Okay, the last two there are man-made. Many of these will vary a little bit depending on where you are in the country or the world, so they're sort of a rough estimate as to where our radiation comes from, and generally speaking they don't cause us as humans a problem. So you just need to remember at least, say, 2 of those types as to where that radiation comes from. Right, more on the nature of radiations. This is higher tier stuff. It can be a little bit tricky. Make your own notes on this. If we start with the left-hand picture, it shows a magnetic field, and the dots kind of indicate the magnetic field coming towards you. You don't have to understand that too much. Basically what it shows is that gamma rays go in a straight line. They are uncharged and therefore are not affected by magnetic fields. Only charged particles are affected by magnetic fields. Alpha go left, beta go right. What that tells someone is that they are different charges. If you understand the rules of magnetism, it works out that beta are negative and alpha are positive. You don't need that at all. That's triple stroke AS physics in actual fact, so we're touching a little bit on some AS physics there. Beta are more curved than alpha because beta are lighter particles, so the magnetic field finds it easier to change their direction. So the heavier, more massive alphas go more in a straight line. The right hand picture shows an electric field. This one's a little bit easier to understand because the rules of electricity are like charges repel, unlike charges attract. So the beta is attracted towards the positive plate, which means it must be negative. The alpha is attracted towards the negative plate, which means it must be positive. And the gamma rays go straight through, which again confirm that they have no charge. The alpha is not deflected as much as the beta, so they're heavier. And the beta, being lighter, are deflected more. Similar idea to the magnetic field really. You notice they'll both go in the same direction. So it's worth reviewing that and making sure you can make your own notes as to the directions of deflection and what they all mean to positive and negative charges and uncharged particles. So I would review that and make some simple notes about alpha, beta and gamma rays and what the deflections tell us about their mass and charges. Okay, moving on to the next slide. The structure of the atom. Bottom picture shows someone called Ernest Rutherford, who effectively you might say is the father of the nuclear atom. But before Rutherford there was a bloke called Thomson and a few other scientists who knew that there were things called electrons, but they didn't know where they were, and so basically as atoms were neutral, they said all the positive and negative charges in the atom somehow spread throughout it, a little bit like a Christmas pudding, and the negative electrons are like currents in that pudding, just spread randomly through the whole mass. So what you've actually got is a solid, like snooker ball of material, or maybe not a snooker ball of material, no one really knew what it was to be honest, but some solid mass of material with negative bits throughout it. Rutherford, being a scientist, wasn't quite sure about that. Some people weren't sure about it either and needed to test it, so he came up with test that he could use, and what he did we'll come to later. He called this one the plum pudding model, and Ernest Rutherford decided that he was going to do an experiment to try and sort that out, which strangely is called the Rutherford Scattering experiment. And what happened was this: he got two people to do it for him. You might recognize the names, Geiger and Marsden. They invented the Geiger counter so that they could actually do this experiment, and they got alpha particles which they could get from a radioactive source. They're very fast moving and they're positive, and they're quite big particles. They were discovered to be the nucleus of a helium atom, and they directed them towards a really thin gold sheet and just fired the alpha particles through the thin gold sheet, used their Geiger-Müller tube which they built, and counted how many alpha particles went through the sheet. The whole thing had to be done in a vacuum because the alphas are absorbed by 3 centimeters of air, so they wouldn't have got through the gold foil to the detector. And the alpha source was also surrounded by a very solid lead sheet with a little gap in it, so that only a thin beam of alpha particles could be directed at the gold foil. So this is a sort of picture of the apparatus. A collimator just means something making a very fine beam, and what the idea was, they just detected the number of alphas coming through. To start with, they used this thing called a zinc sulfide screen which made a flash, but they found that counting the number of flashes was extremely difficult, and so they ended up making their Geiger-Müller tube which turned each flash into a electric sort of pulse which they could then count, or get something to do the counting for them. And effectively that's what they did. They moved the microscope or the detector around and counted the number of alpha particles that went through. What they expected, if the plum pudding model was right, which means there's no solid mass of material, it's spread throughout the whole atom, was that the alpha particle would just go straight through and not be deflected at all, or be deflected by very little when it hits one of these electrons. There was nothing for it to hit really, it's just going straight through an atom which has no, which is just one whole structure. There's no sort of solid bit in the middle or anything. As good scientists, they decided to check their results, and so they moved the microscope all the way round, and what they then discovered was they got one or two alphas that somehow had bounced off something in the nucleus or something in the atom and come back, and they weren't really sure about that. So most went straight through, as in the diagram. Some were deflected through large angles, which wasn't expected, and some were deflected through a very, very large angle. In other words, some of them came backwards. How could that be explained? Well, Rutherford looked at the results and he said, right, if most go straight through without any problem, that means they're not hitting anything. Okay, so that could be empty space. If some are being deflected by a large angle, they must be hitting something. If something, or some, and very, very few are coming back through 180 degrees, they must be hitting something quite big and quite heavy because they're bouncing off it. Also, that thing must be positive because it's repelling the positive alphas. Remember, like charges repel. So it can't be negative. It's not the electrons it's hitting then. So what Rutherford decided was, most of the atom must be empty space, but there must be a very, very small, very, very heavy central nucleus which must be positive because the positive alphas are hitting it and bouncing back. So he then decided that the mass of an atom is not spread uniformly through the whole size of the atom. It's concentrated in a small positive nucleus. Even at this time, in about 1914, they didn't know about neutrons. So Rutherford's first nuclear atom is just a positive nucleus surrounded by negative electrons. It wasn't until about 1936 that the neutron was discovered, and the whole sort of atom as we now recognize it, with protons and neutrons and electrons around the outside, was now sort of put forward and fairly well accepted in actual fact. So what we have then, as a way of explaining these particles either being deflected by large amounts, and 1 in 8,000 it was roughly, being deflected by a huge amount, is that the atom is a small, super dense central positive nucleus surrounded by the negative electrons orbiting in shells. And that's our accepted model with the addition of the neutrons. So we've got our electrons weighing nearly nothing, or a very small mass. The proton's positive with the mass the same as a neutron, and we give that a relative atomic mass of 1. Neutron, same mass as a proton roughly, relative atomic mass of 1. So what we have is a central nucleus, very heavy, particles close together, and then the electrons quite a way outside. To give you a sense of scale, if you think of Wembley Stadium and you put a little golf ball in the middle of Wembley football stadium, that would be the nucleus, and the first electron would be like a small mosquito flying outside the stadium. Most of an atom is empty space, which is quite amazing. Okay, so here's a little summary chart of the atom. We say relative mass, we're not really interested in the real masses, they're very small. So you just make sure that you remember this particular table. It's very useful later on in the course. So proton mass 1, charge 1, neutron mass 1, charge 0, electron relative mass 0-ish, and charge -1. We come back to this nomenclature which you've noticed in the periodic table, the top number being the mass number, the number of protons and neutrons, the middle symbol, He, this case standing for helium, and the bottom 2 is the proton number, which obviously is the number of protons. That actually tells you what it is. 4 minus 2 gives you the number of neutrons, in this case 2. It will be very important, this, and we'll come back to this symbol and the letters later on. Isotopes, just another quick little topic. An isotope is an atom with a different number of neutrons but the same number of protons. So here's 3 isotopes of oxygen. They've all got 8 protons because there wouldn't be oxygen otherwise, but they've got different numbers of neutrons. So if we look at oxygen 16, it's got 8 protons and 8 neutrons, giving it a relative atomic mass of 16. If you look at 17, it's got 8 protons and 9 neutrons, giving it a relative atomic mass of 17. And if you look at oxygen 18, it's got 8 protons and 8 neutrons, sorry, 10 neutrons, giving it a relative atomic mass of 18. On the periodic table you tend to just get quoted the most common stable isotope usually, which in this case would be oxygen-16. The other two are unstable. There's an imbalance in protons and neutrons, and they would emit radiation, likely to be beta in this case. Okay, so we've already said that actually. How many neutrons does each one have? You can sit and just go through that one again. So oxygen-16, 8 neutrons, oxygen-17, 9 neutrons, and oxygen-18, 10 neutrons. Okay. Right, another radioisotope that is radioactive and is actually used in carbon dating, which we'll come back to in another tutorial, is carbon-14. Notice we don't talk about the number of protons. We're actually only interested in the isotope, which is the number of protons and neutrons when we actually talk of this. So hence oxygen-16, oxygen-17, carbon-14. It's just a way that physicists discuss elements.